Okay, now we will look at the isolated forward converter analysis. So in this part, we will investigate or calculate the parameter within the isolated forward converter. Okay, before we start, I want all of you to familiarize with this table. This is a table that we will use a lot to calculate the parameters for forward converter. As you can see here, this is how we can calculate the primary current, transistor power losses, inductor power losses. Okay, then next one here in this slide, this is the calculation of total power losses. This is the formula, the input power, output power, and efficiency. Okay, so all of this is considered the efficiency related Vout loss. And this table here is the non-efficiency related Vout loss, the one that I mentioned due to the leakage inductance, and we have the overlap period, okay, during the turn on of the MOSFET. So this is the table that we can use. Okay, and usually for the equation, you don't have to remember all the equation will be given. You just need to know when to apply the equation. Okay, as I mentioned, this is the losses due to the leakage inductance. And this is the continuation of that. The output voltage, the final output voltage that we can get after the reduction of the output voltage due to the leakage inductance. All of these have their own equation. Okay, this is the first example of the isolated forward converter calculation. So in this case, we are given several values. The first one is the input voltage. So the input voltage here is given 200 volt, and we have, this is the turn ratio of the reset winding, the primary winding, and the secondary winding. So the ratio is 100 to 100 to 10. Okay, and then we have the first diode, second diode, and here, because the value is given, the R inductance, so we will take into consideration when we calculate the loss. And then we also have the capacitor here, and then we have the output current. The switching frequency is 50 kHz, and the duty cycle is 0.3. And these are all the parameters that we have. The inductor here, 2 millihenry. The R inductor, the resistance of the inductor is 0.04. The RDS on, the resistance during the switch turn on, is 0.3. And then we have the leakage inductance referred to the secondary. We have 2 microhenry. Okay, small value, microhenry. This one is millihenry. And then we have the forward voltage of the diode. Okay, for both D1 and D2, we have 0.9. Okay, this is the voltage across the diode when the diode is forward bias. Okay, so we have to determine, first one is the isolated forward converter output voltage, the isolated forward converter efficiency, and the MOSFET voltage requirement. Okay, as the input voltage already given, so we straight away we can write E in equals to 200 volt. The transformer primary turn ratio is 100, and the secondary is 10. Okay, the secondary current will be equals to the output current. So it is given our output current is 10 ampere. So the secondary current maximum Is max is equal to 10 ampere, and the primary current maximum, okay, is the current at the primary. It is not given, so we have to calculate. So we have to calculate based on the Is max. Is max multiplied by Ns over Np, we will get 1 ampere. So we have 1 ampere of output current maximum at the primary circuit. Okay, this one also given the transistor switch duty cycle 0.3, and after we get all of this, we can calculate the V out ideal. So the equation is E in multiplied by D switch multiplied by Ns over Np. So the answer is 6 volt. And then the output current, okay, like I mentioned before, this is 10 ampere because it's already given. The R inductor is given at 0.04. So based on this, we can calculate the inductor resistant power loss, PR inductor. So the equation is, when we say the losses related to resistance, so you must remember that it is the I square R. Okay, so we have the I inductor RMS square multiplied by R inductor. Okay, and then for the I inductor RMS is equal to I out. Okay, I out square multiplied by R inductor, and when you calculate, you will get 4 watt. The voltage drop, like I mentioned before, is given at 0.9 volt, and the rectifier D1 and D2 maximum current, okay, because the diode current is equal to the output current in the secondary circuit, so IAK max will be equals to I out, which is 10 ampere as well. Okay, for the isolated forward converter, because the D1 and D2, okay, D1 will conduct for 0.3 second, and the rest of it will be conducted by D2, okay, for the remaining 0.7. So the total of D rectifier will be 1. And then the combined D1 and D2 power loss will be the D rectifier multiplied by IAK max multiplied by the voltage, the forward voltage, and you will get 9 watt. Okay, next we have to calculate the power losses due to the transistor. Okay, and then we have the transistor on state resistance RDS on, which is 0.25 given in the question. And then we have the transistor current IDS will be equals to IP max, and we already calculate IP max, which is equal to 1 ampere. The transistor RMS current, okay, this one you have to know the equation, the IDS RMS, okay, because the top one is the IDS maximum, okay, but you have to remember the IDS is not conducted for the whole switching period, okay, it's only conducted when the switch is turned on, okay, and the equation will be IDS RMS will be equal to square root of D switch multiplied by IDS max, and in this case our IDS RMS is equal to square root of 0.3 ampere. And then we have the transistor power loss, the P switch is equal to IDS RMS square multiplied by RDS on, okay, and because we have the IDS RMS equal to square root of 0.3, we have to square that and then multiply by 0.25, so it will be 0.3 multiplied by 0.25, which is equal to 0.075. And then we have the total power loss equals to the power loss due to the R inductor, and then due to the rectifier, and due to the switch. We have 4 plus 9 plus 0.075, and the total power loss is 13.075. And then we have the output power. Okay, output power is equal to I out multiplied by V out, and this is the equation for efficiency. We have P out divided by P in. Okay, the P out is we have 10 multiplied by V out. Okay, because I out multiplied by V out, and we don't know yet the value of V out. Okay, and then for the efficiency we have P out divided by P in. P in is equal to P out plus all the losses that we have. So in this case our losses is 13.075. Our P out is equal to 10 multiplied by V out. And then we have the leakage inductance, in this case 2 microhenry, and we have the output voltage overlap loss, delta V overlap, is equal to L leak multiplied by I out multiplied by switching frequency. And if you replace everything, okay, switching frequency is 50 kilohertz, and then L leak is 2 micro, I out is 10. We have the delta V overlap is 1 volt. Okay, and then we have V out equation is V out ideal minus delta V overlap multiplied by the efficiency. So if you can see that this, you have to minus first the ideal voltage, we have to minus the delta V overlap, okay, and then multiply by efficiency to get the V out. Okay, and then we have the equation here, V out equals to 5 multiplied by the efficiency. Okay, and then we have 5 multiplied by efficiency here is all of this equation here. Okay, and then when you can factor out, okay, V out, you have to move everything to this side. Okay, and then the remaining one is 50 minus 13.075 divided by 10, and then you will get 3.6925. Okay, now I will show you how we can derive the previous equation that we used in the previous slide. Okay, first of all, we know that the output power is equal to output current multiplied by output voltage, and then we also know that the efficiency is equal to output power divided by input power, and then the input power is just output power plus the total power losses that we have in the circuit. And then this is, you have to know this, that the V out in this case is equal to V out ideal minus delta V overlap multiplied by the efficiency. So if we don't have the problem with the leakage inductance, we don't have this term, okay, but because we have the leakage inductance, we have to minus the delta V due to the leakage inductance, and then only then we have to multiply by the efficiency. Okay, now we have the efficiency, we can replace with all of this, okay, at this part, and then we have the P out, you can replace with this one. P out is equal to I out times the V out. You have to replace at this point and this point. Okay, after that we can move all of this denominator here to the left side, okay, and multiply by V out here. V out multiplied by this one equals to this equation multiplied by this one. Okay, and then from this we know that we can cancel out the V out here. V out term can be cancelled out, and then we remain with this equation. Okay, then we can move this P loss total to the right side, okay, here, and then after that we can move the I out to this side. So the remaining V out equation is this one: V out ideal minus delta V overlap times I out minus P loss total divided by I out. So if you see from the previous slide, this is the final equation that we use to find the V out. So now we move to the second part of the question, which is to find the isolated forward converter efficiency. Okay, to find the efficiency, we know the equation already. This is the 10 multiplied by V out divided by 10 multiplied by V out plus the 13.075. Okay, so this is the total power losses. This is just the output power, okay, divided by the output power plus the total power losses. Okay, the 13.075 is the total power losses. Okay, so if you add all of this, this is the input power. So the efficiency will be this one divided by the output power plus the total power losses, and at the end you will get 73.85%. So this is the efficiency of the converter. And then for the MOSFET voltage requirement, okay, this is the equation you have to use: the E in, the input voltage, multiplied by 1 plus NP over NR. Okay, so this is the voltage that will occur at the MOSFET, the maximum voltage. So you have to use E in multiplied by 1 plus NP over NR, and this you will get 200, okay, multiplied by 2, so 400 volt. So you have to make sure that the voltage or rating for the MOSFET that you will use is equal to 400 volt. So if you use less than this, so most probably your MOSFET will burn out, okay, and damage. Okay, now we move to the second example. In this example, we have E in equals to 15 volt. The output current is 5 ampere. We have switching frequency 150 kilohertz. Duty cycle is 0.4. We have reset winding, primary winding, and secondary winding set to 10, 10, and 6. For this example, we have the MOSFET RDS on 0.2, and then the forward voltage 0.4. The inductor here is 50 microhenry. The R inductor is 0.1, and we have the leakage inductor refer to primary. Okay, but this is important. If it mentioned refer to secondary, this is the normal one that we have, but now it's refer to primary. Okay, so you need to find the L leakage refer to the secondary. So this refer to primary is set at 1.5 microhenry. We have the capacitor value. This one is set at 220 microfarad, and the equivalent series resistance, this one, is 0.02. So in this example, we have to find or compare the isolated fault converter ideal and real output voltage. Okay, now we have to find the ideal output voltage. So this is the equation for ideal output voltage, in which we have to multiply the duty cycle, multiply by input voltage, and multiply by the turn ratio, and secondary divided by and primary. And then we have this value: V out ideal equals to 3.6 volt. Now we can use the table to find the real output voltage. Okay, so in this side we have the 15 volt, the primary and secondary turn ratio, and then we have the secondary current maximum. So this is equal to the output current. And then for the primary current maximum, IP max, is equal to I out multiplied by NS over NP, and then we get 3 ampere. Okay, next we have to find the transistor power losses. Okay, this is due to the switching losses. We have D switch multiplied by I out square multiplied by NS over NP square multiplied by RDS on. So this one is just the current at the primary, okay, because we have the I out square multiplied by NS over NP. This is just to get the value at the primary side, okay. So 0.4 multiplied by 5 square multiplied by 6 over 10 square multiplied by 0.2, and you will get 0.72 watt. Okay, we know already the output current, and then we have the value of inductor resistance, which is 0.1. So based on this, we can find out the power losses due to the inductor resistance. So this is I out square multiplied by R inductor, then we get 2.5 watt. Okay, and then we have the rectifier D1 and D2 voltage drop VF. So this value is given at 0.4 volt, and then the maximum current, okay, because both are conducting at the output side, so the maximum current that occur is 5 ampere, the same with the output current. Okay, and we have to remember that for isolated fault converter, the D1 and D2, the combined duty cycle is 1. Okay, because during the switch on, D1 will turn on, and during the switch off, D2 will turn on. So the total combined duty cycle for rectifier is 1. And the combined D1 and D2 power losses is, okay, we have the duty cycle 1 multiplied by I out multiplied by VF, which is equal to 2 watt. Okay, now this is new compared to the first example. We have the capacitor ESR, so this is the equivalent series resistance. So in this you have to find the inductor ripple current. Delta inductor is equal to E in multiplied by D switch divided by L out multiplied by F switch, and then this one you have to multiply with the NS over NP. Okay, so when you replace all the value here, you get 0.48 ampere. And then to calculate the equivalent series resistance power loss, you have to use this equation, which is delta I inductor square divided by 12 multiplied by ESR, and then you will get this value 0.384 milliwatt, okay, which is very small and can consider negligible because this is 0.384 milliwatt. Okay, it's very small. So when you compare with 2 watt, this one is nothing. Okay, so you can just mention that this capacitor power loss is negligible. Okay, now we already calculate all the power losses, so we can have the total power losses, which consists of the power losses due to the MOSFET, the power losses due to the R inductor, and due to the rectifier and the equivalent series resistance of the capacitor. But as we know that this one is negligible, so we just add all the other three, and then it come out with the total of 5.22 watt. Okay, for this example, we calculate the input power using this equation. The input power is equal to E in multiplied by D switch multiplied by IP max. Okay, and you will get 18 watt. And the output power can calculate using P in minus P loss. Okay, we have P in equals to 18 minus P loss 5.22, you will get 12.78, and then the efficiency is P out divided by P in, and when you divide this one by this one, you get 71%. Okay, so this one actually you have to multiply by 100. Okay, so it's not mentioned here, but you have to know that for the efficiency the value will be in percentage. The ideal output voltage, V out ideal, is equal to this one multiplied by this switch multiplied by NS over NP, and you will get 3.6 volts. So this is the ideal output voltage, and then we have the value already for the leakage inductance, 1.5 microhenry. So remember that I mentioned earlier in this example that the value that has been given is the L leakage referred to the primary. Okay, so you have to find the leakage inductance referred to the secondary. So to do that, you have to multiply by NS over NP squared. Okay, when you solve this equation, you will get 0.54 microhenry. Okay, and then you can find the delta V overlap. Okay, the voltage drop due to the overlap. And then from this equation, the L leak secondary multiplied by I out multiplied by F switch, you will find that the output voltage overlap or delta V overlap is 0.405. Okay, and then for the output voltage, the final output voltage or the real output voltage is the V out ideal minus delta V overlap multiplied by the efficiency, and then when you substitute everything, you will get the output voltage is 2.27. Okay, this is example number 3. Here we have E in equals to 30 volts, and then we have the reset winding 2, the primary and secondary winding is set to 2 and 1. We have I out equals to 50 ampere, V out equals to 5. Switching frequency is 50 kilohertz. These are the provided equation. Okay, and then the question asks, the isolated fault converter shown was designed idealistically to provide 5 volt output. Okay, so the measurement indicate that the output voltage is 4 volt, and then the efficiency is 90%. Okay, so now in this question we measure. Okay, the question said that the measurement indicates, so they measure the output voltage at this point, so they take the multimeter and put at this point, and the measurement indicate that it is 4 volt. Okay, and then based on the efficiency, so how they can calculate the efficiency, so they measure the input power and then the output power. Okay, they measure the input voltage and the input current of this primary circuit, and then they measure the output voltage and output current, so based on that they can determine the efficiency. So the designer adjusts the duty cycle assuming that losses to be the cause. Okay, because now they already measure the output power and the input power. They measure the efficiency at 90%. So remember that the designer measure the output voltage to be 4 volt, so they think that this might be due to the efficiency issue. Okay, so they adjust the duty cycle to compensate the efficiency, but the output voltage still remain low at 4.5 volt. So instead of reaching 5 volt, it remain low at 4.5 volt. So the first question is determine the original or ideal and adjusted duty cycle. Number 2, suggest and justify by calculation a possible cause for the low output voltage. Low mean this one, not reaching 5. And then finally provide a design solution. Okay, now for the first question, determine the original or ideal and adjusted duty cycle. So for the ideal duty cycle, the equation is like this, and then when you replace all the value, okay, to find the D switch, so you know that the ideal duty cycle is 0.333. Okay, so this without taking any consideration of the efficiency. So based on this, we already know the E in, we already know the NS and NP, and the ideal one that we want to achieve is 5 volt. Okay, so based on this, we have to find the D switch. So this is the ideal duty cycle. So the D switch that we have is 5 divided by 30 multiplied by NP over NS, which is 2, and you will get 0.333. So ideally, if we put this switch equal to 0.333, if the circuit didn't have any losses or any other issue, you will get the output voltage equals to 5. Okay, so now we have this switch equals to 0.333. Okay, but we know that by the measurement, okay, the designer measure the efficiency to be 0.9, 90%. Okay, so he take into consideration the efficiency term in this equation and recalculate the D switch. Okay, so all other parameter are the same, but now we have the efficiency parameter in the equation. So when he put this parameter in the equation, he get the duty cycle of 0.37. So this is the supposed duty cycle that supposed to increase the voltage to 5 if the reason is only due to the efficiency. Okay, so you get the value of 0.37. So now we already determined the original ideal duty cycle and the adjusted duty cycle, which is 0.37. Okay, now for the second part, suggest and justify by calculation a possible cause for the low output voltage. So in this case, we know that in isolated forward converter we have the problem of leakage inductance overlap. Okay, so this might be the reason why after we adjust the duty cycle we still cannot get the required value, which is 5 volt. So we know that when we have the delta V overlap, the equation will be like this: V out ideal minus delta V overlap multiplied by the efficiency. So when we want to solve this, the V out ideal, okay, is equal to this one. Okay, and then we have the 30 multiplied by 0.37. This is the duty cycle after we adjust. Okay, when we think that the efficiency is the problem, we adjust to this value, and then this is the NS over NP, and then we'll get 5.55. Okay, so this is the ideal output voltage without the efficiency term. Okay, because we have to calculate this one. Okay, now we already adjust, remember we already adjust the duty cycle to 0.37, so the ideal output voltage have to use the 0.37, so we get 5.55. so we know that there are delta V overlap term here, and we know that the efficiency is 0.9. Okay, so to calculate this we also have to assume that, the efficiency remain the same for whatever duty cycle that we use. The efficiency is assumed to remain the same at 0.9. Okay, only then we can calculate the value, okay, for this question. Now when we have the output voltage, we can calculate by using this equation. 5.55 is equal minus delta V overlap multiplied by 0.9 is equal to 4.5. So we know that the output voltage, remember that when the duty cycle is increased to 0.37, the output voltage still remain at 4.5, so we have to use this value. Okay, now we want to find the value of the delta V overlap here, because we know that in this equation the only parameter that we don't know is the delta V overlap. So we can find the delta V overlap by rearrange this equation. So the value that we get is 0.55. So this is the amount of delta V overlap, okay, due to the leakage inductance, 0.55. Okay, now we have to find the leakage inductance, because we know that the delta V overlap, which we already calculated just now, is equal to L leak multiplied by I out multiplied by the switching frequency. So now we can determine this L leak, the leakage inductance, because this one we already know 50 ampere, this one we already know this is 50 kilohertz. So we can find the L leak here. So the L leak equals to 0.55 divided by 50, and then this one multiplied by 50 kilohertz, and you will get 0.22 microhenry. Okay, remember that we have this equation. So the delta D switch is equal to L leak multiplied by I out, and then multiplied by F switch, okay, and then divide by E in minus VDS times NS over NP. Okay, in this equation the VDS, okay, the voltage during the switch turn on is not given, so we assume that this is negligible, so you can just use the E in. Okay, this is the full equation, but this one the value is not given and we cannot determine that, so we can assume that this is 0. Okay, now we can calculate the delta D switch. Okay, and then when we substitute all of this value into this equation, we will get the value of 0.037. Okay, so this is the amount of duty cycle that we need to adjust, okay, to attain the required value that we want. Okay, so the adjusted duty cycle is 0.37, and then we have to adjust by 0.037, and the duty cycle that we need to use is 0.407. Okay, so now we need to verify whether our solution can solve the problem. So we know that the duty cycle that we need to use is 0.407. Okay, and then we know that this equation to find the output voltage, V out ideal minus delta V overlap multiplied by efficiency. Okay, and then when we plug everything, okay, this one 30 minus multiplied by 0.407 multiplied by 1 over 2 minus the delta V overlap 0.55, and everything multiplied by the efficiency. Then when we calculate all of this, we will get the value of 5 volt. Okay, that's all the 3 examples that I want to show you for this chapter. So if you want to learn more or do more exercise, you can go to the portal and search the courses CET 4 to 6 from previous or past years. So there you can find all the solution for tutorial and then for the test and final exam. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.